Did you know that right now, as you breathe, the universe is dying? Not a dramatic, explosive death, but a slow, silent, almost imperceptible death, like music gradually turning down until it becomes just a whisper, and then ... eternal silence. Hello, it's me here again, and today I want to take you on a journey through the deepest time imaginable. Where are you right now? Maybe relaxing at home, or perhaps walking while listening to this. It doesn't matter. What matters is that you're here, conscious, alive, in an extraordinary moment of cosmic history. Before we begin this adventure through the universe's destiny, help me with something simple. If this content sparks your curiosity about the mysteries of the cosmos, consider subscribing to the channel and leaving a like on this video. It helps me continue bringing these scientific and philosophical journeys to more people who, like you, are fascinated by the great enigmas of existence. Now, take a deep breath with me. Feel the air entering your lungs, air that carries atoms that were once part of distant stars, unexplored planets, comets that danced through space for billions of years. You are connected, intimately and profoundly, with the entire universe. And it's about the destiny of this universe that we're going to talk tonight. We'll explore together one of the most fascinating and melancholic theories about how everything that exists will come to an end, the Big Freeze, or as scientists call it, the heat death of the universe. But before we begin, let me ask a question that might seem simple, but carries within it all the complexity of the cosmos. Have you ever stopped to think that the universe we live in isn't eternal? That everything we see, the stars that shine like beacons in the darkness, the galaxies that spin in majestic cosmic dances, the very light that allows us to see, all of this might have an end? Not an explosive and dramatic end like a great cosmic collision or catastrophic collapse, but a silent, gradual end like a song that keeps getting softer, more spaced out, more subtle until it becomes just a whisper, and then ... silence, a universe that doesn't end with a bang, but with a final, eternal, cold sigh. This is what we'll talk about tonight. About a future so distant that our human mind can barely comprehend its vastness, when the last atom will have danced its last dance, when the last particle of light will have traveled its last mile, when the very concept of event will become obsolete because nothing will happen anymore, ever again, anywhere. Does it sound scary? Maybe. But there's a deep and melancholic beauty in this story, a cosmic poetry that invites us to reflect on our existence, on the value of each moment, on the extraordinary miracle of being here, now, conscious and alive in a universe that pulses with energy and possibilities. So get more comfortable, let your muscles relax, allow your breathing to become slower and deeper. Let's begin our journey through deep time, exploring the mysteries of the Big Freeze and discovering what this theory teaches us not only about the cosmos, but about ourselves. Imagine for a moment that you could hold the universe in your hands as if it were an infinite and translucent fabric. You would feel its texture not smooth like silk, but undulating, flexible, alive. This fabric has a name you may have heard before: space-time. It's the very structure of reality, the stage where all cosmic history unfolds. Now, while you hold this imaginary fabric, something extraordinary happens. It begins to stretch. Not violently or abruptly, but with hypnotic constancy, like the slow breathing of a sleeping giant. Each point on the fabric moves away from all other points, not because something is pushing them, but because the very space between them is growing, expanding. This is the most profound and transformative discovery of modern astronomy. The universe is expanding. Not expanding into something larger because there's nothing larger, but expanding within itself, creating more space where there was no space before, more time where there was no time before. Have you ever wondered how we know this? How can we be certain that something as vast as the entire universe is really growing? The answer lies in the light from stars that reaches us like cosmic messengers, carrying stories from places and times unimaginably distant. When we observe a distant star, its light comes to us slightly reddened, not because the star is red, but because the space through which the light traveled expanded during the journey. It's as if the light itself were stretched along with the fabric of space-time, its waves becoming longer, redder. Astronomers call this redshift, and it's our window to understanding cosmic expansion. But here's the mystery that brought us to the Big Freeze theory. This expansion isn't slowing down. S would be natural if gravity were trying to pull everything back together. On the contrary, it's accelerating. Every second that passes, the universe expands a little faster than in the previous second. It's as if there were an invisible force, a mysterious energy that permeates all space and pushes everything away from everything else, each time with more intensity. Scientists gave this force a poetic and enigmatic name: dark energy. We don't know exactly what it is. It represents one of the greatest mysteries of modern physics. But we know it constitutes about 70% of everything that exists in the universe. Think about this for a moment. More than 2/3 of the universe are made of something we can't see, touch, or fully understand, but that is actively shaping the destiny of everything that exists. It's as if we were living in a symphony where most of the music is played by invisible instruments. This accelerated expansion has profound consequences. It means that galaxies are moving away from each other faster and faster. Billions of years from now, a distant galaxy that today we can observe with our telescopes will have moved so far away that its light will no longer be able to reach us. The observable universe, the part of the cosmos we can see, is paradoxically shrinking even while the total universe grows. Have you thought about this before? That we're living in a special epoch of cosmic history when we can still see other galaxies, when the night sky is still dotted with light from distant places? In the deep future, hypothetical observers will see only darkness where today we see the majestic Milky Way stretched across the sky. But accelerated expansion is just the first act of our cosmic story. To truly understand the Big Freeze, we need to dive deeper, exploring another fundamental concept: entropy, the universe's irreversible tendency to move toward disorder and thermal equilibrium. Close your eyes for a moment and imagine a hot cup of coffee in your hands. You can feel the heat spreading through the porcelain, warming your palms. You can hear the steam rising in invisible spirals, carrying with it the rich, comforting aroma. Now observe what happens. Slowly, gradually, the coffee cools. The heat disperses into the surrounding air, mixes with the ambient temperature, until coffee and air reach the same thermal state. This simple daily observation reveals one of the most fundamental laws of the universe, the second law of thermodynamics. Heat always flows from hotter to cooler, energy always disperses from concentrated to spread out, order always tends toward disorder. And this happens irreversibly. You'll never see heat from the air spontaneously concentrate back into the coffee, making it hot again. Physicists gave a name to this universal tendency: entropy. It's a measure of disorder, of energy dispersion, of how spread out things are in a system. And the second law of thermodynamics tells us something both simple and profound: the entropy of the universe always increases. But what does this mean on a cosmic scale? It means the entire universe is going through the same process as your coffee cup. All the energy that exists, the light from stars, the heat of planets, the movement of galaxies, is slowly dispersing, spreading out, diluting in the vast ocean of space-time. Have you ever stopped to think about what stars really are? They're gigantic nuclear furnaces, converting hydrogen into helium and releasing energy in quantities that defy our imagination. A single star like the Sun produces every second more energy than all of humanity has produced in its entire history. But even stars are subject to the tyranny of entropy. Each photon of light that a star emits carries with it a bit of its ordered energy and spreads it through space. It's as if the star were slowly melting, losing its energy concentration to the surrounding universe. And when a star finally exhausts its nuclear fuel, it dies, sometimes silently, sometimes in a spectacular explosion, but always contributing to the increase of cosmic entropy. Imagine for a moment the universe as a vast ballroom where trillions of dancers, atoms, particles, photons, perform a complex choreography. In the beginning, when the universe was young, the dance was ordered, energetic, full of patterns and structures. But as time passes, the dancers get tired, their movements become more random, more dispersed. The music of creation still plays, but each time softer, more diffuse. This is the melancholic beauty of entropy. It's not a destructive force in the traditional sense. It's not like a hurricane that destroys a city or an earthquake that shakes mountains. Entropy is more subtle, more patient. It's like an invisible artist who, brushstroke by brushstroke, transforms a detailed and vibrant painting into a canvas of uniform color, without contrasts, without surprises. And here we reach the heart of the Big Freeze theory. If entropy always increases, if energy always disperses, if the universe is expanding and cooling, then there's an inevitable final state toward which everything is heading. A state where all usable energy will have been consumed, where there will be no more temperature differences, where nothing more can happen because there will be no more available energy to make anything happen. Physicists call this final state the heat death of the universe. But perhaps death isn't the right word? It's more like a deep, eternal sleep, where everything exists but nothing happens, where time loses its meaning because there are no more changes to measure it by. Can you feel the magnitude of this idea? That everything we know, our Earth, our Sun, our galaxy, even the most massive black holes, is inexorably moving toward this final state of thermal equilibrium. It's not a race, but a slow, hypnotic walk through billions and billions of years. But don't worry yet. We're just beginning to unfold this cosmic story. And like every good story, it has many chapters, many surprises, many moments of unexpected beauty before reaching its silent end. Let's take a time trip, you and I, not to the past, but to the future, a future so distant that our human mind can barely process it. We're now 100 trillion years from now. Yes, you read that correctly, 100 trillion years. To put this in perspective, the current universe is only 13.8 billion years old. We're talking about a future that is to our era what our era is to the first minutes after the Big Bang. You're floating in intergalactic space, observing what remains of the cosmos. What do you see, or rather, what don't you see? The first thing that catches your attention is the luminous silence. The great spiral galaxies we know, the Milky Way with its gracefully curved arms dotted with stellar nurseries, Andromeda with its trillions of stars dancing in gravitational harmony, all of them merged long ago into giant elliptical structures, immense islands of light, separated by ever-growing oceans of darkness. But even these merged galaxies are different. They're darker, redder, like ancient bonfires where only the embers still glow weakly. Why? Because young, blue stars are no longer being born, those luminous giants that used to illuminate the cosmos with their bright white light. Do you remember how stars are born? In vast clouds of gas and dust, where gravity slowly pulls material to form increasingly dense clumps, until the pressure and temperature at the center become so intense that they initiate nuclear fusion. It's a process that requires raw materials, hydrogen, mainly the simplest and most abundant element in the universe. But after 100 trillion years, almost all usable hydrogen has been consumed. The massive stars, those cosmic furnaces that shone with the intensity of millions of suns, long ago exploded in spectacular supernovas, scattering their heavy elements through space and then collapsing into black holes or neutron stars. Medium-sized stars like our Sun evolved into red giants, then expelled their outer layers forming colorful planetary nebulae, and finally became white dwarfs, stellar cores the size of Earth, but with the mass of an entire star. And the small stars, the red dwarfs? These are the stubborn survivors of the cosmos. They burn their fuel so slowly, so sparingly, that they can live for trillions of years. In this distant future we're visiting, they're practically the only stars still alive, small red spheres that shine with a soft, constant light, like solitary candles in a vast and empty cathedral. But even these last sentinels are reaching their end. One by one, they exhaust their hydrogen, briefly expand as tiny red giants, and then contract to become white dwarfs. It's like watching the last act of a cosmic play that lasted hundreds of trillions of years. Can you imagine the melancholy of that moment? The last normal star in the universe slowly flickering, its red and weak light becoming fainter and fainter until it finally goes out. It's not a dramatic explosion, but a gradual fading, like music that lowers its volume until it disappears into silence. And then, what remains? White dwarfs scattered through space like forgotten pearls in a broken jewel. Neutron stars slowly spinning, their magnetic pulses becoming weaker and more spaced out. Black holes of all masses, from the small remnants of stars to the supermassive ones that once governed the center of galaxies, now floating alone in the growing darkness. But the story doesn't end here. White dwarfs, although they no longer produce nuclear energy, are still hot, incredibly hot. They shine not because they burn fuel, but simply because they radiate the heat accumulated during billions of years of nuclear fusion. It's like an iron you turn off, but that still remains hot for a while. And so these white dwarfs begin the slow, very slow journey of cooling. They radiate their thermal energy to the surrounding space, photon by photon, like a heart that gradually slows its beats. First they shine white, then yellow, then orange, then red, then ... nothing. Black dwarfs, objects the size of Earth but with the mass of a star, cold as the surrounding space, invisible except for the gravitational distortion they exert on light passing nearby. This cooling process takes longer than our mind can understand. We're talking about quadrillions of years just for a white dwarf to cool significantly. It's a time so vast that it makes the current age of the universe seem like the blink of an eye. And you know what's most fascinating? Even in this incredibly distant future, when the stars have disappeared, the universe still won't have come close to its final state. The true journey toward the Big Freeze is just beginning. Let's continue our journey through deep time. Now we're in an even more distant future, so distant that numbers begin to lose meaning for our human experience. We're talking about 1,034 years in the future. To put this in an impossible perspective, if every second since the Big Bang were an entire universe, and every second of that universe's existence were another universe, and we continued this cosmic multiplication several times, we still wouldn't come close to this number. In this unimaginably distant future, even the white dwarfs, those last vestiges of the stars we knew, have cooled completely. They are now black dwarfs, frozen objects floating in absolute darkness. No more light is being produced anywhere in the universe. No nuclear fusion happens, no star shines, no energy is generated. The cosmos has become a vast cemetery of cold and inert objects. But something extraordinary is happening, something that defies our intuition about the permanence of matter. The very atoms that compose these cold objects, atoms that seem so solid and permanent, begin to behave strangely. They begin to dance a very special quantum dance. Do you remember quantum mechanics? That fascinating and counterintuitive theory that tells us that, at the most fundamental level, reality is probabilistic, not deterministic. A particle isn't in a specific place, but in a probability cloud of being in various places. And occasionally, very occasionally, this probability allows seemingly impossible things to happen. One of these quantum impossibilities is what physicists call quantum tunneling. Imagine an electron trying to climb an energy mountain that classically would be too high for it to scale. In classical physics, the electron would be trapped forever at the base of the mountain. But in quantum mechanics, there's a small, tiny probability that the electron will simply appear on the other side of the mountain, as if it had built a tunnel through it. Now, you might be wondering, what does this have to do with the universe's destiny? Everything. Because when we have enough time, and I'm talking about time periods that make the current age of the universe seem like less than a nanosecond, even the tiniest probabilities eventually manifest. In this distant future, atoms and the cold objects begin to use quantum tunneling to reorganize their structure. It's as if they were playing a cosmic game of solitaire, reshuffling their configurations until they find the most stable arrangement possible. And what is this arrangement? Iron. Iron has the most stable atomic nucleus that exists. It's the element that requires the least energy to keep its protons and neutrons together. So, over incomprehensible periods of time, all the elements in the universe, the carbon in our bodies, the oxygen we breathe, the silicon in rocks, the gold in our jewelry, all of them slowly, atom by atom, transform into iron through spontaneous quantum processes. Imagine this. Our Earth, which today is made of a rich variety of elements, will eventually become a perfect sphere of cold iron. The mountains we admire today, the oceans where life flourished, the cities we built, everything will transform into the same uniform and inert substance. But the quantum dance doesn't stop there. Iron isn't eternally stable either. Given enough time, time measured on scales that make our previous journey seem like an instant, even iron nuclei begin to spontaneously decay. Protons, those particles that seem to be the fundamental and indestructible building blocks of matter, reveal their mortality. This is one of the most profound and melancholic aspects of the Big Freeze theory. Not even matter is eternal. Everything made of atoms, you, me, stars, planets, galaxies, all of this is temporary. Not temporary on the human scale of decades or centuries, nor even on the cosmic scale of billions of years, but temporary on a time scale that defies any concept of permanence we might have. When protons finally decay, they disintegrate into simpler particles, electrons, positrons, neutrinos, photons, and these particles in turn spread through the expanding universe, diluting into an increasingly thin soup of energy and matter. Have you ever tried to imagine what it means for there to be no more atoms? No more structures, no more objects, no more things, in the sense we understand? It's a universe reduced to its most fundamental expression, solitary particles wandering through distances so vast that they rarely or never encounter other particles. And yet, even in this apparently final state, the cosmic story hasn't ended. Because while all this happens, there still remain in the universe those objects that seem to be the final tombs of everything, black holes. And they hold their own surprises, their own chapters in the long narrative of the Big Freeze. Have you ever wondered what happens when even matter ceases to exist? When only black holes remain floating in infinite darkness? Let's find out together. We're now at a moment in cosmic history so distant that our human language can barely describe it. Protons disintegrated incomprehensible eons ago. There's no more ordinary matter in the universe, no more atoms, no more planets, no more dead stars. Everything that once had solid form has dissolved into a thin mist of fundamental particles scattered across unimaginable distances. But we still haven't reached the end of the story. Floating alone in absolute darkness, like extinguished lighthouses in an infinite ocean, are the last vestiges of a cosmos that was once vibrant and full of life. Black holes. These fascinating objects that have captured our scientific and popular imagination for decades. Regions of space-time where gravity is so intense that not even light can escape. They're the cosmic champions of mass concentration. They can contain the mass of millions or billions of suns, compressed into a region smaller than our solar system. In this remote future, they are the last rulers of the universe. Some are small, born from the collapse of massive stars trillions of years ago. Others are gigantic, the supermassive black holes that once inhabited the center of galaxies, swallowing stars and gas with voracious appetite. Now, all of them float alone, separated by distances so vast that they rarely exert gravitational influence on each other. Can you imagine the cosmic loneliness of these objects? They're like solitary gods of a forgotten pantheon, each reigning over their own empty domain with no subjects to govern, no matter to consume. They distort space-time around them, creating deep gravitational wells, but these wells are empty traps. There's nothing left to fall into them. For a long time, physicists thought black holes were the most permanent objects in the universe. After all, they seem to be gravity's final word. Once something falls beyond their event horizon, it can never escape. They were considered the final cosmic trash cans, ultimate destinations for all the matter and energy in the universe. But then, in the 1970s, a young theoretical physicist named Stephen Hawking made a discovery that would forever change our understanding of black holes and the universe's destiny. Using the principles of quantum mechanics, he showed that black holes aren't completely black. They emit radiation. How is this possible? How can something that not even light can escape emit radiation? The answer lies in the quantum nature of the vacuum. What we call empty space isn't really empty. It's a seething sea of quantum activity, where particle-antiparticle pairs spontaneously appear from nothing and then annihilate each other in fractions of a second. Normally, these quantum fluctuations are invisible to us. But near a black hole's event horizon, something interesting happens. Sometimes a particle-antiparticle pair forms so close to the horizon that one of the particles falls into the black hole while the other escapes. To a distant observer, it appears that the black hole is emitting radiation, Hawking radiation. This radiation is incredibly weak. For a black hole with the mass of the Sun, the temperature of Hawking radiation is less than a billionth of a degree above absolute zero. much colder than the cosmic background radiation that permeates the universe. But in the distant future we're visiting, when cosmic expansion has made the universe even colder, this radiation becomes significant. And here's the most extraordinary aspect. When a black hole emits Hawking radiation, it loses mass. It's as if each emitted photon carries away a tiny piece of the black hole's substance. Einstein taught us that mass and energy are equivalent. So when energy escapes as radiation, the black hole's mass decreases. This means that black holes, these last bastions of cosmic permanence, are slowly evaporating. They're becoming smaller, less massive, until they disappear completely in a final flash of radiation. The time it takes for a black hole to evaporate completely depends on its mass. Small ones evaporate more quickly, large ones take longer. A black hole with the sun's mass would take about 1,067 years to evaporate completely. But supermassive black holes, those monsters that once devoured entire galaxies, can take 10,100 years or more. These numbers are so vast that our human mind simply can't process them. If you wrote the number of years needed for the largest black hole to evaporate, using one digit for each atom in the observable universe, you still wouldn't have enough space to write the complete number. But even these unimaginable periods eventually pass. In the end, one by one, black holes begin their final moments. An evaporating black hole is like a candle consuming itself. The smaller it gets, the faster it burns. In the final stages, the process accelerates dramatically, and the black hole disappears in a final explosion of particles and radiation. Imagine watching the last black hole in the universe disappearing. For trillions and trillions of years, it was the last macroscopic object in the cosmos, the last structure, the last thing you could point to and say, there's something there. And then, in its final moments, it briefly glows, a tiny point of light in a universe that long forgot what it means to shine before fading away forever. Can you feel the magnitude of that moment? It's like the last sunset of a world that will never see morning again. The last chord of a cosmic symphony that lasted longer than any concept of eternity we can imagine. And then silence, absolute darkness. The universe becomes a vast ocean of solitary particles, electrons, positrons, neutrinos, photons, separated by distances so enormous that they can spend eons without encountering other particles. Is this the final state? Have we finally reached the big freeze? We're now in what cosmologists call the particle era, a period of cosmic history so distant in the future that it makes all the numbers we've mentioned so far seem small. There are no more black holes, no more organized matter of any kind. The universe has become a rarefied gas of fundamental particles floating through a space that continues expanding inexorably. But what kind of particles are these? Mainly electrons, positrons, neutrinos, and photons, the final products of the long decomposition of all the complex matter that once existed. They travel through the vacuum like ghosts of a cosmos that was once vibrant, each following its solitary trajectory through infinite darkness. The density of this cosmic soup is almost inconceivable in its thinness. If you could mark a cube of space 1 light year on each side, a distance so vast that light takes an entire year to travel it, you might find only a few lost particles floating inside. It's as if the universe were an ocean where each drop of water was separated from all others by entire continents of emptiness, and in this almost empty ocean, something curious happens. Remember quantum mechanics and its strange probabilities? Even in an apparently dead universe, these probabilities continue operating. Occasionally, very, very occasionally, two particles meet. An electron crosses the path of a positron, and they mutually annihilate in a tiny flash of light. Or maybe two photons, traveling for eons through the void, collide and briefly create an electron-positron pair before it too annihilates. These events are incredibly rare. The time scales between them are so vast that they make black hole evaporation seem fast. We're talking about periods measured in 10,150 years or more between significant events. If every second were a universe, and every second of that universe were another universe, and we continued this progression for dozens of levels, we still wouldn't come close to these timescales. But there's something deeply poetic about these rare collisions. They're like sparks from a fire that long ago went out, ghostly reminders that, even in the coldest and emptiest possible state, the universe still preserves a thin echo of its ancient vibrancy. Each particle-antiparticle annihilation is like a word whispered in an infinite and silent library. And here we come to a fascinating question. Is this really the universe's final state? Have we reached the true big freeze where nothing more can happen? For a long time, physicists thought so. It seemed we had reached maximum entropy, the state of absolute thermal equilibrium, where no usable energy remains in the system. But nature has even more surprises in store for us. Because even in this apparently final state, the laws of quantum mechanics continue operating. And these laws tell us something extraordinary. Given enough time, any possible configuration of particles will eventually occur spontaneously. Imagine this. At some incredibly distant moment in the future, the particles floating through empty space might, by pure quantum coincidence, momentarily organize into more complex patterns. Maybe some will group together to form a simple hydrogen atom. Maybe on a timescale that defies any concept of patience, they might even organize into even more complex structures. This phenomenon is known as quantum fluctuation, and it suggests that even in the coldest and deadest possible universe, there's always a minuscule probability that something interesting will happen. It's as if the cosmos, even in its state closest to death, still occasionally dreams of life. Have you ever wondered if the universe can dream? If, in these rare and brief fluctuations, it reenacts echoes of its lost youth? There's something almost conscious about this capacity of the cosmos to reinvent itself, even when it seems to have exhausted all its possibilities. But these fluctuations lead us to even deeper questions about the nature of time, existence, and possibility. Because if any configuration of particles can eventually occur, then theoretically, you could encounter yourself again, reorganized from the quantum vacuum, in a future so distant that even numbers lose meaning. Let's pause for a moment and contemplate one of the most dizzying and beautiful ideas in modern physics. We're talking about Poincare's recurrence theorem, a mathematical discovery that tells us something extraordinary about isolated systems, like our universe. The theorem tells us that any closed system with finite energy, given enough time, will eventually return arbitrarily close to any previous state it has ever occupied. In other words, if you wait long enough, any specific configuration of particles can repeat itself. This means something almost impossible to believe. At some moment in the incredibly distant future, the particles in the universe might reorganize exactly or almost exactly the same way they're organized now. You might be sitting in the same position, reading these same words, having exactly the same thoughts. But don't get too excited about the prospect of immortality. The time needed for this to happen is called Poincare recurrence time, and for a system the size of the observable universe, this time is approximately 10,101,070 years. To put this in perspective, if you wrote the number 1 followed by zeros, where each zero was smaller than an atom, you'd still need more matter than exists in the observable universe to write this number. It's a period of time so vast that it makes all the other timescales we've discussed seem instantaneous. Black hole evaporation, proton decay, the current age of the universe, all of this is less than the blink of an eye compared to recurrence time. But there's something deeply moving about this possibility, however remote it may be. It means that information, your thoughts, your conscious experience of this moment is never completely lost. It disperses, dilutes, hides in the quantum dance of particles, but theoretically can reorganize again. It's as if the universe were an infinite book where each page tells a different story. But occasionally, very occasionally, the same story repeats. Or maybe it's more like a cosmic dream, where the sleeping cosmos occasionally relives memories of when it was awake and vibrant. Imagine meeting yourself again in a cosmos reborn from quantum randomness. You would have the same memories, the same feelings, the same questions about the universe's destiny. But would it really be you, or just a quantum copy floating in a sea of possibilities? This question leads us to the heart of some of the deepest mysteries of consciousness and identity. What makes us unique? Is it the specific arrangement of atoms in our body, the pattern of neural connections in our brain, or something more subtle, more fundamental? In the perspective of the Big Freeze, these questions gain a cosmic dimension. If all the universe's complexity, including life, consciousness, love, art, everything we consider important, can eventually resurge from quantum vacuum fluctuations, then perhaps there isn't really a final end. Maybe there are just very, very long pauses between acts of an infinite cosmic play. But these remote possibilities of recurrence bring us back to a fundamental question. What does end really mean when we talk about the universe's destiny? Because even when we reach what seems to be the coldest, emptiest, deadest possible state, quantum mechanics whispers to us that the story might not be over. There's still another possibility, one last surprise that the cosmos might have in store for us. What if the vacuum itself, this nothing that permeates all space, weren't really the lowest possible energy configuration? What if there were an even more fundamental, even more stable state waiting to be discovered? Have you ever thought about the possibility that our entire universe is just a temporary bubble in something even larger and more permanent? A local fluctuation in a true vacuum that we don't yet understand? It's an idea both terrifying and wonderful that even our concept of final end might be just another illusion of our limited perspective in time and space. Let's breathe deeply together at this moment. Feel the air entering your lungs, carrying with it oxygen that was once part of distant stars, ancient plants, other beings that breathed long before us. There's something comforting in knowing that we're connected, through the most basic substance of life, with all of cosmic history. But now I want to take you to explore something even more fundamental than the air we breathe, more basic than the atoms that compose us. I want to talk about the vacuum itself, this nothing that fills the space between all things. For a long time, we thought the vacuum was exactly that, nothing. Absolute emptiness, total absence of anything. But quantum mechanics taught us that this intuition was wrong. The vacuum is, in fact, a place of frenzied activity, an effervescent sea of possibilities that appear and disappear on timescales smaller than any possible measurement. Imagine the vacuum as a perfectly calm water surface seen from afar. From a distance it seems smooth, motionless, empty. But get closer, much closer on the scale of quantum events, and you'll see that the surface is constantly agitated by tiny waves, by droplets that emerge from nothing and immediately return to the sea. These waves in the quantum sea are pairs of virtual particles, and antiparticles that sprout spontaneously from the vacuum's energy, exist for incomprehensibly brief periods of time, and then mutually annihilate, returning their energy to the vacuum. It's as if empty space itself were constantly imagining particles, briefly dreaming of materiality before returning to its fundamental state. And here's something extraordinary. These vacuum fluctuations aren't just theoretical curiosities. They have real, measurable effects. They influence the behavior of atoms, cause forces between nearby metal plates, the Casimir effect, and even contribute to the black hole evaporation we discussed earlier. But in the context of the Big Freeze, vacuum fluctuations take on an even deeper meaning. Because when we reach the apparent final state of the universe, when all matter has dispersed, when all black holes have evaporated, when only solitary particles remain in expanding space, these fluctuations become practically the only activity left in the cosmos. It's as if the universe had reduced itself to its purest expression, a field of pure possibilities, where reality constantly plays with the idea of manifesting itself, but most of the time remains only as unrealized potential. Can you imagine the strange beauty of this state? A cosmos where the only music is the silent symphony of virtual particles, dancing their invisible quantum dance on an empty stage that extends to infinity. It's like a cosmic orchestra playing for an audience that long ceased to exist. But that continues playing because that's the fundamental nature of reality. But these vacuum fluctuations lead us to an even deeper question. If the vacuum is constantly creating and destroying virtual particles, if it's always boiling with quantum activity, then it possesses energy. And Einstein taught us that energy and mass are equivalent. This means that the vacuum itself has mass, has energy density. And here we arrive at one of the most disturbing discoveries of modern cosmology. The vacuum might not be in its lowest energy state. There might be even more stable configurations, even lower energy states than the vacuum we know. Physicists call this false vacuum versus true vacuum. If our entire universe exists in a false vacuum state, this means it's only temporarily stable. Like a ball balanced on top of a hill, it can stay there for a long time, but eventually it will roll down to the true valley. And when that happens, if it happens, it would be the most absolute end we could imagine. The transition from false vacuum to true vacuum would create a bubble of true vacuum that would expand at the speed of light, completely annihilating everything in its path. It wouldn't just be the death of matter and energy, it would be the rewriting of the very laws of physics. An entire universe erased and replaced by something completely different. But here's the comforting aspect, if we can use that word. If this were to happen, we could never predict or detect it. The bubble of destruction would travel at the speed of light, so there would be no advance warning. One moment we'd be here, the next, we wouldn't even not be. There simply would be no more being. It's a possibility both terrifying and strangely peaceful. Like falling asleep without knowing you're falling asleep, like an instantaneous and total turning off of lights in a play that didn't even know it was being performed. But maybe, just maybe, our vacuum is really stable. Maybe we're already in the cosmos's fundamental state, and all these concerns about true vacuums are just speculations from curious minds, trying to imagine even more extreme possibilities than the Big Freeze. Now I want to invite you to an even more challenging imagination exercise. We're approaching what might be the true heart of the Big Freeze, and to understand it completely, we need to confront something our human mind instinctively rejects, the idea of infinite time. Close your eyes and try to imagine forever. Not 1,000 years, not 1,000,000, not even the impossible numbers we've talked about so far. Imagine a time that never, ever, under any circumstances, will come to an end. A forever that really means forever, without exceptions, without escape routes, without happy or unhappy endings, just eternal continuity. It's almost impossible, isn't it? Our mind, shaped by the experience of lives that begin and end, of days that dawn and dusk, of seasons that come and go, simply doesn't have the mental structure to process true infinitude. It's like trying to see a color that doesn't exist or hear a sound beyond all possible frequency. But this is exactly what the Big Freeze presents us, a universe that doesn't end. Never ends. It just continues, state after state, in eternal expansion through a space that always grows, always cools, always becomes emptier and more silent, but never stops. Imagine being a solitary particle in that future universe. You're an electron, let's say, floating through a vacuum that extends in all directions for distances that make light years seem microscopic. You travel and travel and travel. Occasionally, maybe every 10,100 years, you encounter another particle. You interact briefly, maybe annihilate each other in a tiny flash of light, or maybe simply pass by each other like ships in the cosmic night. And this continues forever, not just for a very long time, literally forever. Each moment extends to the next, which extends to the next, which extends to the next, in a chain that has no end because the concept of end has lost all meaning. There's something deeply melancholic about this perspective, but also something strangely liberating. Because if time is really infinite, if the universe never really dies, but just transforms into something increasingly simple and dispersed, then maybe our anxiety about endings is unnecessary. Think about it. In our daily life, much of our anguish comes from awareness of mortality, of finitude, of the fact that all good things must come to an end. But what if the universe showed us a different way of existing? A way where there's no end, only transformation? Where death is just a word we use to describe changes we don't fully understand? In the Big Freeze, nothing really dies in the sense of ceasing to exist completely. Energy is conserved, it just disperses. Information is conserved, it just spreads out. Particles continue existing, they just become more solitary. It's like music that doesn't stop playing, but gets softer, more spaced out, more subtle, until we can only hear it if we pay very, very close attention. And here's a perspective that might completely change how we see our own existence. If the universe can persist through such dramatic changes, from the immense density of the first moments after the Big Bang to the almost total dispersion of the Big Freeze, then maybe persistence, continuity, is a more fundamental property of reality than we imagined. Maybe our own consciousness, our capacity to experience and reflect on the universe, is also something more persistent than we think. I'm not talking about personal immortality in the traditional sense, but something more subtle, the idea that the universe's capacity to know itself through conscious beings, like us, might be a characteristic that manifests in different ways throughout its infinite development. Have you ever wondered if it's possible that, at some point in the incredibly distant future, forms of organization we can't even imagine might emerge from quantum fluctuations? Information structures based not on atoms and molecules, but on more fundamental energy patterns? What if consciousness were a property as basic to the cosmos as gravity or electromagnetism, always finding ways to manifest itself, no matter how different the universe becomes? It's a possibility both speculative and deeply hopeful. It suggests that even in the coldest and emptiest scenario we can imagine, the universe might retain its capacity to surprise itself, to create novelty, to generate forms of complexity we can't yet conceive. But even if that never happens, even if the Big Freeze is really the final state of reality, there's something paradoxically comforting in its infinitude. Because it means there will never be a moment when we can say, now it's over. Now there's nothing more. There will always be more time, more space, more possibility, even if dispersed across unimaginable distances. Here we are, my fellow cosmic traveler, in the middle of our exploration of the Big Freeze, and I feel it's time for a contemplative pause. Not to rest our bodies, though you can certainly adjust your position, maybe pull a blanket over your shoulders if you're feeling cold, but to allow our minds to process the magnitude of what we're discovering together. Because what we're really exploring isn't just the physical destiny of the universe. We're exploring the boundaries of meaning itself. We're confronting questions that touch the core of how we understand existence, purpose, value, and hope. Imagine for a moment that you could time travel and tell an ancient philosopher, say, Heraclitus, who said we can't step in the same river twice, about the Big Freeze. How would he react to the idea of a cosmos that changes so slowly that it eventually almost stops changing? What irony would there be in discovering that the universe, which seemed to be the very embodiment of constant change, might eventually reach a state of near permanence? Or consider how this cosmic perspective illuminates different philosophical traditions about time and eternity. Buddhists speak of infinite cycles of existence, of samsara that has no beginning or end. There's something almost Buddhist about the idea of the Big Freeze, a state where change becomes so subtle, so spaced out in time that it approaches cessation without ever really ceasing. The Stoics, in turn, taught about the importance of accepting what we can't control, of finding peace in contemplating our smallness before cosmic forces. What more Stoic perspective could exist than accepting that our entire universe is walking toward a state of maximum dispersion, and that this is simply the nature of things? But perhaps the philosophical tradition that most resonates with the Big Freeze is existentialism. Because if there really is no final cosmic purpose, if the universe isn't going anywhere except toward a state of thermal equilibrium, then it's we who must create meaning in our temporary existence in this slowly unraveling cosmos. There's something deeply liberating about this perspective. If the universe doesn't have a master plan, if there's no grandiose destiny toward which everything moves, then each moment of consciousness, each experience of beauty, each act of love or creativity gains special weight, not because it serves a greater cosmic purpose, but precisely because it doesn't serve one. Because it's genuinely ours, genuinely human, genuinely free. Have you ever thought that maybe life's beauty comes exactly from its impermanence? That a rose is beautiful not despite withering, but because it withers? That music moves us not despite ending, but because it ends? The Big Freeze offers us this perspective on a cosmic scale. Maybe the universe is beautiful precisely because it's temporary, because its stars go out, because its galaxies disperse, because even its fundamental particles eventually find silence. And this leads us to an even deeper question. What does tragedy mean on such a vast time scale? In human experience, we call something tragic when something valuable is lost prematurely. But premature in relation to what? If a star shines for 10 billion years before going out, is that premature? If a galaxy dances for 100 trillion years before dispersing, is that tragic? Maybe our intuition about tragedy is simply inadequate for cosmic scales. Maybe the universe operates in a completely different aesthetic dimension from ours, where concepts like short and long, early and late, gain and loss simply don't apply. Or maybe, and this is a possibility that fascinates me, the very concept of value is something that emerges only at certain scales of time and complexity. Maybe the universe isn't intrinsically valuable or valueless, but becomes valuable precisely when it develops the capacity to value itself through conscious beings like us. In this perspective, each moment of consciousness in the cosmos is like a candle lit in an infinite cathedral. The cathedral doesn't exist for the candle, nor does the candle exist for the cathedral. But when the candle is lit, it illuminates a small space around it, creates shadows that dance on the walls, generates heat that can be felt by those who approach. And when the candle goes out, the cathedral returns to its natural darkness, but it was, for a brief moment, a place where light existed. This metaphor seems to capture something essential about our cosmic situation. We're not the universe's purpose, but we're one of its most interesting accidents. We're not here to save the cosmos from the big freeze. There's nothing to be saved. Because there's nothing intrinsically wrong with a cold and dispersed universe. We're here to be the temporary experience the universe has of itself as something warm, complex, and conscious. Let's now take a more intimate journey through the stages of the Big Freeze, no longer as distant observers contemplating impossible timescales, but as if we were sensitive witnesses to a long and gradual farewell. Because that's what the Big Freeze really is, a farewell. The slowest, gentlest, most melancholic farewell imaginable. Imagine you could accelerate your perception of time, so you could watch the entire future history of the universe like a slow-motion movie. What you would see would be something like a great symphony coming to an end, where the instruments stop playing one by one. The music becomes increasingly simple, until only a long, constant note remains. And then, not silence exactly, but the softest possible sound, almost inaudible but still present. First, you would see the stars going out, not all at once, but gradually like lights in a city seen from afar during a blackout that spreads slowly. The blue giants, those cosmic bonfires that burn with fierce intensity, would be the first to leave. They live fast and die young on the cosmic scale. Then the yellow stars like our sun, going through their red giant phase before contracting into white dwarfs. Finally, the small red dwarfs, those shy candles of the cosmos, that would continue shining long after all the others had gone out. You would see galaxies moving away from each other, not like a violent explosion, but like a silent farewell of old friends who know they won't see each other again. The Milky Way and Andromeda, those two majestic spirals that today dance toward each other, would first merge into a single giant elliptical galaxy, and then that merged galaxy would find itself increasingly isolated in an expanding cosmos. And within those solitary galaxies, you would witness the slow emptying of complexity. Planets that orbited their stars for billions of years would eventually be disturbed from their orbits, either by the death of their host stars or by rare gravitational encounters with other stars. Some would be ejected into intergalactic space, to wander eternally as cosmic orphans. Others would fall into black holes or be torn apart by tidal forces. There's something particularly touching about the idea of these orphan planets. Imagine worlds that perhaps once harbored life, maybe had oceans and atmospheres, maybe were the stage for stories as rich as our own, floating alone through the intergalactic void. Without a star to warm their surfaces, they would become frozen spheres carrying with them only the frozen memories of warmer times. But complexity's farewell doesn't stop at planets. Eventually, even matter's most basic structures would begin to unravel. You would see entire mountains, which seemed so permanent and solid, slowly dissolving as the atoms in their rocks began to undergo quantum tunneling, reorganizing into more stable configurations. It's hard to imagine mountains evaporating, isn't it? But on sufficiently long timescales, even Mount Everest would become a cloud of dispersed particles. Not through erosion or tectonic activity, but through the very quantum instability of ordinary matter. As if solid reality were just a temporary illusion, a mirage that dissipates when observed for long enough. And you would also watch the slow death of atoms themselves. Each proton, each atomic nucleus that seemed so fundamental and permanent, would eventually succumb to quantum instability. It's like watching nature's library being dismantled letter by letter, word by word, until only the most basic characters remain floating isolated in a vast empty space. But perhaps the most poetic aspect of this slow farewell is how it preserves the dignity of each complex structure. There's no violence in the big freeze, no sudden destruction. Each star has time to burn all its fuel. Each atom has time to find its most stable configuration. Each particle has time to explore all the possibilities of its existence before following its solitary path through the cosmos. It's as if the universe were a cosmic gentleman, allowing each of its creations to live its complete life before gently saying goodbye. There's a cosmic courtesy in the big freeze, an infinite patience that allows everything to end at its own pace, without hurry, without pressure. And in this patience, in this cosmic gentleness, maybe we find a lesson about how to face our own smaller farewells. If the universe can allow its stars to shine for billions of years before silently going out, maybe we can learn to give ourselves and each other the time necessary for our own transitions, our own transformations. Because the truth is that we're all participating in our own version of the big freeze. Our bodies are constantly exchanging atoms with the environment. Our cells die and are replaced. Our thoughts arise and dissolve. We are temporary structures of complexity in a constant flux of change, not different from stars or galaxies, just operating on a different timescale. What if we could learn to see our own impermanence with the same serenity with which the cosmos faces its final destiny? If we could find beauty not only in what endures, but in what transforms, if we could celebrate not only arrivals, but also farewells. We're approaching the end of our cosmic journey, but before we get there, I want to share with you one of the most beautiful parables about the universe's destiny ever written. It's a story by science fiction master Isaac Asimov called The Last Question. In it, through eons of technological evolution, humanity repeatedly asks the same question to increasingly advanced computers: how can entropy be reversed? And always, invariably, the answer is insufficient data for a meaningful answer. Until, at the end of time, when the universe has finally succumbed to complete heat death, when nothing remains but the final cosmic computer, it finally finds the answer, and demonstrates it by creating a new universe, pronouncing the words, "Let there be light." It's a fascinating story because it suggests that maybe the end isn't really the end. That maybe the big freeze is just a pause between movements of an even greater symphony. That maybe our universe is just one of many, each going through its own cycle of birth, evolution, and heat death, before giving rise to the next. This possibility leads us to some of the deepest questions in modern cosmology. Is our universe unique or part of a vast multiverse where countless cosmos are born, evolve, and die on timescales that make our own cosmic history seem instantaneous? Some theories suggest that new universes can spontaneously arise from quantum fluctuations, even in the emptiest vacuum. Others propose that black holes might be tunnels to other universes, that each extreme gravitational collapse gives birth to a new cosmos on the other side. There are even theories suggesting that our own Big Bang might have been the result of the final evaporation of a black hole in a previous universe. Can you imagine this perspective? A cosmos where the end is always also a beginning? Where one universe's heat death is the birth event of the next? It's like an infinite cosmic breathing, exhalation and inhalation, contraction and expansion, end and beginning, in cycles that extend beyond any concept of eternity we can understand. But even if our universe is unique, even if the big freeze is really the end of everything, there's something deeply comforting in the temporal perspective this theory offers us, because it shows us that end is always relative to the time scale we choose to observe. On a human scale, our life seems brief, a few decades of consciousness in a cosmos of billions of years. But on a cosmic scale, even the trillions of years it will take for stars to go out are just an initial moment in the universe's long history. And on the scale of the big freeze, even black hole evaporation is just the first act of a play that continues for periods that defy any attempt at understanding. This teaches us something important about perspective. When we feel overwhelmed by the brevity of human life, we can remember that we're part of a much longer story. But when we feel insignificant before cosmic vastness, we can remember that even the cosmos itself is impermanent, that even the universe is subject to change and transformation. And maybe that's exactly where the special value of our conscious existence lies. We're not important because the universe was made for us or because we serve some grandiose cosmic purpose. We're important because, for a brief moment in the cosmos's long history, matter organized itself in such a way that it can contemplate itself. For a cosmic instant, the universe developed eyes to see itself, mind to understand itself, heart to be moved by its own beauty and mystery. At this exact moment, as you read these words, you are one of the most complex forms of organization the universe has ever produced. Your brain, with its billions of neurons forming trillions of connections, is one of the most sophisticated structures known in nature. Your capacity to contemplate questions about cosmic destiny, to be moved by the beauty of a scientific theory, to find meaning even in the face of universal impermanence, this is extraordinary. And when we think about the Big Freeze, when we imagine that distant future where only solitary particles remain floating through the void, maybe we should see this not as a tragedy, but as a natural and even beautiful conclusion to a story that had the incredible luck to include chapters like us. Because even if the universe eventually becomes cold and empty, it will have been, for a time, warm and complex and conscious. Even if the stars go out and galaxies disperse, they will have shined and danced and created heavy elements that allowed life to emerge. Even if our own species is just a momentary flash in cosmic history, we will have been the way the universe knew and admired itself. And here we are, my dear cosmic travel companion, reaching the end of our exploration of the Big Freeze. But like every good story about the universe, our end is also a beginning, the beginning of your own reflections on everything we've discovered together tonight. Breathe with me one more time. Feel the air filling your lungs, carrying with it atoms that were once part of distant stars, ancient planets, other creatures that contemplated the same skies we contemplate. You are literally made of stardust, as astronomer Carl Sagan said. But now we know that this stardust has a destiny. Eventually, it will return to the cosmic void from which it came, but not before having participated in the extraordinary adventure that is conscious existence. During our journey tonight, we traveled through timescales that challenge human imagination. We saw how the universe can continue existing long after all stars go out, long after all black holes evaporate, long after all matter decomposes into fundamental particles. We contemplated a cosmos where time almost loses all meaning because almost nothing happens, but where existence still persists in its most fundamental form. And what did we discover on this journey about ourselves? That we are extraordinarily improbable events in a universe that walks inexorably toward thermal equilibrium, that our capacity to think, feel, love, create, and question represents a temporary peak of complexity in a cosmos that inevitably tends toward simplicity. But there's something deeply beautiful about this improbability, like flowers that sprout in a desert, like music that emerges from silence, like light that shines in darkness. Our conscious existence is a miracle, not because it violates the laws of nature, but precisely because it emerges from them. We are what happens when matter and energy organize themselves complexly enough to contemplate themselves. The Big Freeze teaches us that impermanence isn't a flaw in the universe, but one of its most fundamental characteristics. Everything changes, everything transforms, everything eventually moves towards simpler and more stable states. But in the process, patterns of temporary complexity emerge that are genuinely new, genuinely creative, genuinely beautiful. And maybe that's exactly why our existence has value. Not because it's permanent, it isn't. Not because it serves a greater cosmic purpose, maybe it doesn't. But because it represents something genuinely unique in the universe's history, reality's capacity to experience itself subjectively, to question itself, to be surprised by its own existence. Each moment of consciousness you experience, this moment now, as you contemplate these ideas, is a temporary victory of complexity over simplicity, of order over chaos, of information over randomness. It's the universe becoming, for an instant, conscious of itself through you. And this leads us to a paradoxical perspective on our cosmic situation. On one hand, we're insignificant on a cosmic scale, temporary specks of complexity in a vast universe that will exist long after we've disappeared. On the other hand, We're extraordinarily significant. We're the way the cosmos developed the capacity to understand and value itself. This duality, our simultaneous cosmic insignificance and importance, might be one of the deepest lessons the Big Freeze has to teach us. It invites us to cosmic humility, but also to a celebration of conscious life. It encourages us to value each moment of experience, not because these moments are permanent, but precisely because they aren't. If we knew we would live forever, if we knew the universe would always be full of bright stars and vibrant planets, maybe we wouldn't value so much the beauty of a sunset, the intimacy of a deep conversation, the wonder of a scientific discovery. It's impermanence that makes everything precious. And so paradoxically, the Big Freeze, this theory about the ultimate end of all cosmic complexity, can teach us to value more deeply the temporary complexity we're part of. It can inspire us to create, love, question, celebrate with even more intensity, knowing that we are temporary expressions of cosmic creativity. Thank you for accompanying me on this journey through deep time, my friend. Thank you for allowing your mind to extend through impossible timescales, for contemplating questions that touch the limits of what human consciousness can process. You've participated in one of the oldest and noblest human traditions, looking at the cosmos and wondering about our place in it. Now, as our conversation comes to an end, I want to leave you with the question that echoes through all our exploration, the question that resonates both on human and cosmic scales, both in the present and in the incredibly distant future. If the universe is really dying slowly, if everything we know and love is just a temporary phase in a much longer cosmic journey toward cold and final dispersion, what does this change in how you choose to live now, in this extraordinary and improbable moment of consciousness and possibility?